Imagine two clocks, identical, down to the atom. You keep one on the ground floor of a building. You carry the other to the roof. Wait a year. Bring it back down. The clock from the roof is ahead, not by a dramatic amount, by about 90 billionths of a second. But it is ahead, and no one broke it. No one tampered with it. It simply experienced more time than the one downstairs. That is not a rounding error. That is not a flaw in the measurement. That is the actual physical truth of how time behaves in our universe. Most people believe time is the one constant thing. A second here is a second there. A minute on Earth is a minute on the moon. That is a lie. According to current scientific understanding, time is not a backdrop the universe happens inside of. It is a variable, stretched, compressed, and warped by gravity, by speed, and by scale itself. And once you start looking closely, you find that nothing in this universe agrees on what time it is. Not two clocks in the same building, not two planets in the same solar system, not even the two halves of your own body. We tend to think of time the way we think of a ruler, fixed, universal, the same no matter who is measuring it. That assumption is baked into almost everything we do. We schedule meetings across time zones, assuming the rate of time is identical everywhere, just offset by hours. But Albert Einstein discovered something that quietly dismantles that assumption. Time is relative to gravity and to velocity. The stronger the gravitational field you sit in, the slower your clock runs compared to someone farther away from that mass. The faster you move through space, the slower you move through time. This isn't theoretical. It's engineered into your phone right now. GPS satellites orbiting Earth experience weaker gravity than we do on the surface, which speeds their clocks up, and they're moving fast enough that their velocity slows their clocks down. The two effects don't cancel out. Left uncorrected, GPS satellite clocks would drift by about 38 microseconds a day. That sounds small. But uncorrected, your GPS location would be off by around 10 kilometers within 24 hours. Your phone works because engineers built a correction for the fact that time runs differently 20,000 kilometers above your head than it does in your pocket. And that is just the beginning of the discrepancy. Because once you start scaling up, from a satellite, to a planet, to a star, to a black hole, to the universe itself, the differences in how time behaves stop being measured in microseconds. They start being measured in something closer to madness. Let's start close to home. Closer than you think. Your head and your feet are not the same age. Because your head is slightly farther from the center of the Earth's mass than your feet, it sits in a marginally weaker gravitational field. That means time moves very slightly faster at your head than at your feet. Physicists have actually measured this, using atomic clocks accurate enough to detect the difference across a height of about 1 foot. Over an average human lifetime, your head will have aged a few dozen nanoseconds more than your feet. It's an amount too small to matter to you, but it proves something enormous. Time isn't just different between planets. It's different between the top and bottom of your own skull. There is no single now that your entire body shares. You are, in a very literal sense, a slightly time-smeared object. And this is not something we simply theorize about. It's something we've directly clocked. Scientists at NIST built optical atomic clocks precise enough to detect gravitational time dilation across a height difference of a single millimeter. At that resolution, stacking two clocks on top of each other produces a measurable difference in the passage of time between them. Think about what that means. Time isn't a river flowing evenly past everything in the universe. It is a landscape with peaks and valleys, and every object sits at its own unique elevation. While your own body cannot escape this effect, it's negligible enough to ignore. But the moment you leave Earth, the moment you approach the kind of gravity found near a dying star, negligible stops being the right word. Step off Earth, and the disagreements about time get stranger fast. Consider Mercury. On Mercury, a single day, one full rotation relative to the Sun, takes about 176 Earth days. But a Mercury year, one full orbit around the Sun, takes only 88 Earth days. That means a day on Mercury is twice as long as its year. A person born there would celebrate 2 full birthdays before they'd seen a single sunset. Venus is even stranger. Venus rotates so slowly and in the opposite direction to its orbit that its day, 243 Earth days, is longer than its year, which is 225 Earth days. And because of that backward spin, the Sun on Venus rises in the west and sets in the east. These aren't relativistic effects. This is simple orbital mechanics, but it proves something important before we go further. Even without touching Einstein's physics at all, the very idea of a day or a year is a local invention. It only means something relative to the specific planet you happen to be standing on. Now add gravity to the mix. The Sun's gravitational field is far stronger than Earth's. A clock sitting on the surface of the Sun, if such a clock could survive, would run measurably slower than a clock on Earth, purely because of how deep it sits in the Sun's gravitational well. And that's still gentle, cosmically speaking, because the Sun is a lightweight. To see gravity truly bend time, you have to go somewhere the Sun could never survive being. This is where time stops behaving like a suggestion and starts behaving like a trap. Imagine sending a probe toward a black hole while you stay safely behind, watching through a telescope. As the probe approaches the event horizon, the point of no return, something impossible happens from your point of view. The probe appears to slow down, not gradually, dramatically. Its clock, as far as you can tell, appears to be ticking slower and slower, approaching a dead stop. From your perspective, the probe never actually crosses the horizon. It just fades, frozen in time, forever approaching but never arriving. But from the probe's own perspective, nothing unusual happens at the horizon at all. Its own clock ticks normally. It crosses the boundary in a perfectly ordinary instant. And from there, it has only a short amount of its own time left before it reaches the singularity. Two totally different, totally true experiences of the same event. One observer sees eternity, the other sees an ordinary few seconds. Physicists call this effect gravitational time dilation. And near a black hole, it isn't subtle. It's total. Get close enough to the event horizon, and 1 second of your time could correspond to years, centuries, or more passing for the rest of the universe. Spend what feels like an afternoon orbiting near a black hole's edge, and you could return to find that decades, or longer, have passed everywhere else. This isn't science fiction license. It's the direct mathematical consequence of general relativity, and it has never once failed a test we've thrown at it. And here is the part scientists still don't have a full answer for. We don't actually know what happens to time inside the singularity itself. Our equations don't just get complicated there, they break. General relativity predicts a point of infinite density where the rules of physics, including the rules governing time, simply stop applying in any way we know how to calculate. It isn't that we haven't measured it carefully enough. Our current models actively fail at that point. Something is happening to time at the heart of every black hole in the universe, and we genuinely do not know what. Now flip the lens. Instead of speed and gravity, look at scale of a different kind, the sheer, staggering length of Earth's own history. If you compress the entire 4.6 billion year history of Earth into a single 24-hour clock, here is where things would land. Life doesn't appear until around 4 a.m. Complex, multicellular life doesn't show up until around 9 p.m. Dinosaurs arrive at about 10:56 p.m. and go extinct at 11:39 p.m. Anatomically modern humans, all of us, everyone who has ever lived, show up in the final 1.7 seconds before midnight. The Roman Empire, the pyramids, every war, every book, every person whose name you've ever learned in a history class. All of it happened in a sliver of time so thin it barely registers on this clock at all. That's disorienting on its own. But here's the part that reframes everything. Geologists don't experience deep time as a story. They experience it as layers of rock. A single centimeter of sediment can represent 1,000 years of accumulation. A canyon wall can contain 1,000,000 years compressed into a few meters you could touch with your hand. Standing at the bottom of the Grand Canyon, you are physically standing next to nearly 2 billion years of Earth's history, stacked in bands you can count with your eyes. Time, at this scale, stops being something you experience and becomes something you can literally put your hand on. And this deep time isn't finished accumulating. It's still being written, one imperceptible layer at a time, at a pace so slow that no human observer will ever see it move. Zoom out past Earth entirely, and the numbers stop being relatable at all. The universe is approximately 13.8 billion years old. If Earth's history is a single day, the universe's full history would be roughly 3 days on that same scale, and Earth wouldn't even appear until partway through the 3rd day. But the truly disturbing part isn't the past, it's the future. The sun will burn out in roughly 5 billion years. That already feels close to incomprehensible. But stars in general, the very last stars to ever form, won't finish burning out for roughly 100 trillion years. That's not a typo. Trillion. The current age of the universe, 13.8 billion years, is a rounding error compared to the era of starlight still to come. After that comes what physicists call the degenerate era, a universe lit only by the slow, cold glow of dead stellar remnants, stretching for something on the order of 10 to the 40th power years. Beyond even that lies a theoretical possibility that protons themselves, the building blocks of every atom, including the ones in your body, may eventually decay. If that's true, it wouldn't happen for at least 10 to the 34th years, and some estimates run vastly longer. And beyond that, if nothing intervenes, the universe may approach what's called heat death, a state of maximum entropy, where no more usable energy exists to do anything at all. No stars, no chemistry, no motion that matters. Just an unimaginably vast, unimaginably cold, unimaginably empty stretch of true nothing, extending for a length of time so long that all of human history, every civilization, every war, every love story, wouldn't even register as a rounding error against it. We are not living near the beginning of time. We are not living near the end of time. We are living in an infinitesimally brief flicker, closer to the beginning than not, in a universe whose true lifespan makes the word billion feel almost quaint. There's one more scale left, the smallest one, and it might be the strangest of all. Physicists have a unit called Planck time, roughly 5.4 times 10 to the negative 44th seconds. It's derived from the fundamental constants of physics, and it's believed to represent the smallest meaningful unit of time that our current laws of physics can describe. Below that scale, our equations stop making sense, not because we haven't built precise enough instruments. We're nowhere close to measuring anything at that resolution, and may never be. But because, at that scale, quantum mechanics and gravity are both supposed to matter simultaneously, and we don't have a working theory that describes both at once. This has led some physicists to a question that sounds almost philosophical rather than scientific. Does time, as a smooth, continuous flow, even exist at the smallest levels of reality? Or is what we experience as the steady passage of time actually made up of discrete, indivisible ticks, a kind of cosmic frame rate that only look continuous because we're far too large and far too slow to notice the gaps? This is not settled. Our current models don't just lack precision here, they don't agree with each other at all. Some approaches to quantum gravity suggest time is fundamental. Others suggest it might be an emergent illusion, something that only appears to exist because of how particles are entangled with one another, meaning that at the deepest level of reality, time itself might not be a real ingredient of the universe at all, but a side effect of something else entirely. We build satellites that correct for time dilation down to the microsecond, and yet, at the smallest possible scale, we still don't know if the thing we're correcting for is even fundamentally real. Start stacking it all together, and the picture gets almost dizzying. Your head ages faster than your feet. A day on Venus outlasts its year. A probe falling into a black hole experiences an ordinary afternoon while the rest of the universe watches it seem to freeze for eternity. The entirety of recorded human history fits into the last fraction of a second on Earth's own 24-hour clock. The stars still forming today won't finish burning for 100 trillion years, a span so long that the current age of the universe is barely a rounding error against it. And underneath all of it, at the smallest imaginable scale, we're not even certain time is a real, continuous thing rather than something assembled out of indivisible fragments. There is no single, universal now. There never was. What we call time is not one substance flowing evenly through the universe. It is a different local experience for every object, at every scale, depending on how fast it's moving and how deep it sits in a gravitational well, from the top of your head to the edge of a black hole, to the coldest, final moment the universe will ever reach. We like to imagine ourselves as living inside time. The truth, it seems, is closer to the opposite. Every one of us is generating our own private version of it, and the version we experience, brief, linear, and steady, may be one of the least representative versions in the entire universe. Somewhere between the frozen edge of a black hole and the flicker of Planck time, our own lifespan sits, brief, warm, and stranger than it feels. I hope you enjoyed the video. See you next time.